Okay, so for number one, okay, we have Neptune, which orbits the sun. Okay, so we know we're looking at an FC equals FG situation, right? Where we've got mv squared over r. This is the mass of Neptune because it is the orbiting body, right? And then on this side, we have Newton's universal law of gravitation. So we have the mass of the sun times the mass of Neptune over r squared. All right, we are trying to find the speed of Neptune in its orbit. So I need to get v by itself, so I'm going to multiply both sides by r. And when I do that, the squared is going to cancel on the bottom. Okay, so now r is gone. M of Neptune is going to cancel on both sides as well, which is good because I was never given it. And I need to find the v, not the square of v, so I've got a square root. So we're going to have v equals big G, so 6.67 times 10 to the minus 11 times the mass of the sun, 1.99 times 10 to the 30, divided by the radius of Neptune's orbit, 4.50 times 10 to the 12 meters. Okay, so again, you got to be really careful when you're punching this in because there's lots of exponents and stuff like that. So 6.67. All right, so we're looking at 5.43 times 10 to the 3 meters per second. All right, questions on how that one worked? That's one of the easier ones because you didn't have to substitute in and solve for t. Okay. All right, give number. How many people have done number 2? All right, I'll give you a few more minutes on number 2 then, and we'll look at that one. All right, so for question number 2, okay, we've got the moon, Miranda, that orbits Uranus at a speed of 6.68 times 10 to the 3 meters per second. We want to use that and the mass of Uranus, which is given to us here, okay, to determine the orbital radius of Miranda's orbit. All right, well, Miranda is a natural satellite, in other words, a moon, okay, that orbits Uranus. So for anything that orbits something else, FC equals FG. All right, so we have mv squared over r equals big G times mass 1, which will be Miranda, and then Uranus would be our second one, okay, over r squared. All right, this is which mass on this side? Miranda, right? It's always the orbiting mass, so that's that one there. Okay, so it's going to cancel, which is good because we weren't given it anyway, right? But we are solving for r, so I'm going to bring r over to this side, okay, by multiplying both sides by it because that's what I want to solve for. Okay, so when I multiply both sides by r, I'm going to r squared here, okay, and it's going to cancel away. Everybody all right with that? Yeah. Okay, and then I'm going to divide both sides by v squared. Okay, and that should give me my formula. Okay, so r is going to equal 6.67 times 10 to the minus 11 times 8.68 times 10 to the 25 divided by 6.68 times 10 to the 3 squared. All right, everybody all right with that? Whoops. No, that's right. Divided by 6.68, 3 squared. All right, so we're getting 1.30 times 10 to the 8. Awesome. Okay, making sense to everybody there? All right. Now, why would a moon be named Miranda? There's actually a set of rules for naming moons and planets within our solar system. So as they're discovered, they're first just given a number. It's got it's got two letters, which is usually whatever instrument found it, and then the number is like kind of the date it was found on. And then it goes through this whole process where they figure out what name it should get. So for Earth, it's just Luna, okay, which is moon. Okay, for Mars, Mars is the god of what? War. Okay, and what are the two moons of Mars? Phobos and Deimos. Phobos is fear. Deimos is panic. They are the companions of war. Any other thing that would be discovered to be orbiting Mars would have to be given some sort of name associated with the god of war. Okay, Jupiter, okay, is like the Roman name for Zeus, and all of the moons, and there's like 60 of them, are named for the lovers of Zeus. Yeah, Zeus was morally questionable. Anyway, and then around Saturn, okay, Saturn is, all the moons are named for the Titans, okay. For Uranus, they're all Shakespearean characters. So there's like Miranda and Puck and like all these, like there's a bunch from Midsummer Night's Dream. And okay, around Neptune, they all have to have some sort of sea or ocean type of thing. So Triton, okay, is the weapon that Neptune carries. That's the largest moon, so that they all have kind of a ocean theme or a Neptune theme. Okay, and then we talked about Pluto last week. Pluto's the god of the underworld, and its biggest moon is Charon, which is the name of the boatman who sails you across the river Styx to the underworld. Yeah, all the other moons are in that same naming scheme, okay, around that. So yeah, there's actually a set of rules, if you can believe that, for naming things as you discover them. Now you can win that at Trivial Pursuit. So if you ever are playing a trivia game and that comes up, you now know the answer. That's got to be one of the most obscure questions there is, though. Okay, so this one here is going to have a little bit more to do with the substitution stuff we talked about. Okay, so we have Landsat, which is an imaging satellite that takes pictures of the ozone layer and geological features. It orbits Earth at a height of 912 kilometers. What are its orbital speed and period? All right, we're going to solve for period first. Okay, now there's a couple of tricks in this question. First off, we're told it orbits at a height of 912 kilometers. Where's that measured from? That's measured from the surface. Where do we want radius measured from? The center. All right, so the first thing we have to do is calculate the proper radius. So we will have 912,000 meters plus 6.37 times 10 to the 6 meters, okay, the radius of the Earth, all right, to get our actual orbital radius here. Okay, so 912,000 plus 6.37. It's 37 on ours, right? On your formula sheet, it's 37. Yeah? Okay. All right, so there's our orbital radius, 7.282 times 10 to the 6 meters. Okay, and obviously it's orbiting Earth, so we know one of the masses we're going to use is the mass of the Earth. The other mass would be Landsat, but what always happens to the mass of the satellite? It always cancels, so we don't need to know its mass. All right, so then we're going to set this up as FC equals FG. All right, but instead of using mv squared over r, I'm going to substitute in for v, okay, the formula for v, 2 pi r over t. But it's got to be squared, so that'll be 4 pi squared r squared over t squared. All right, but when I do that, one of the r's is going to cancel off with the r on the bottom. All right, so I'll be left with this. Okay, so I'm going to have m 4 pi squared r over t squared equals big G times the mass of the Earth times the mass of the satellite over r squared. All right, so we know the mass of the satellite is going to cancel off both sides. I want to solve for period. Okay, so I'm going to bring period over to this side so that it's on the top. Okay, then I'm going to multiply both sides by r squared. What's r times r squared? R cubed. Okay, and then I'm going to divide both sides by big G times the mass of the Earth, okay, so that they come over here. All right, so when we are plugging our numbers in, so we're going to have 4 pi squared okay, times 7.282 times 10 to the 6 cubed, okay, divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, that's the mass of the Earth, right? And then we're going to square root that to give us T. Okay, everybody follow my manipulation? That is as tricky a manipulation as you will end up with in this unit, right? When you have to substitute in and then solve for T. Okay, so when we do that, all right, so we got 4 pi squared times 7.282, 6 cubed, all right, divided by what's on the bottom, 6.67, the negative 11, times 5.98, 24. All right, so we're getting this number here, and that will be in seconds. Okay, so 3.82 times. Did I not square root it? I did not square root it. Good catch. That's better. Seemed like a long time. Okay, so we have 6,182 seconds, or 6.18 times 10 to the 3 seconds. So just under 2 hours. All right, questions on how that formula works when we have to substitute? Because I can't remember a unit exam in the last 10 years where I did not make a satellite motion question where you had to substitute. Hint, hint. All right. Let's have you guys try those two. They have to do with that substitute. Well, number 1 doesn't have to do with that substitution, but number 2 does. Okay, and watch for, they're both trying to trick you, okay, in that not only are the altitudes given in kilometers, but they are the altitudes, not the orbital radius. All right, so the International Space Station has an orbital altitude or height of 359.2 kilometers. So first thing we have to do is figure out what the actual R is. All right, so we have 359.2 kilometers plus our radius of the Earth, 6.67 times 10 to the 6. Okay, I'm going to convert that to meters when I actually do the addition here. Okay, so there's our radius in kilometers plus 6.6. Whoop, I didn't put brackets around that. .37. All right, so there's our orbital radius, 6.7292. Times 10 to the 6 meters. All right, so now that we know the actual orbital radius, now we can find its orbital speed. Okay, again, FC equals FG. All right, so the mass of the International Space Station is going to cancel. Okay, this R is going to cancel the squared on this R, and then we're going to square root in order to get V. So V will equal 6.67 times 10 to the minus 11 times the mass of the Earth divided by the radius, which we calculated to be 6.7292 times 10 to the 6. All right, so when we do that, we should get 7.69 times 10 to the 3 meters per second. Okay. How many people are done number 2? Okay, I'll give you a few more minutes on number 2. Okay, so remember, for number 2, you do have to substitute. Okay, so for number 2, okay, we have the Xray satellite, and it's taking pictures of high-energy objects in the universe. It is orbiting at 114,593 kilometers. That's really far away, actually. Okay, that's beyond geosynchronous orbit. It needs to be that far away so that the magnetic field of the Earth doesn't interfere with its observations. Okay. We need to find out what its orbital period would be. So we have, again, FC equals FG, except this time, instead of putting in V, we're going to substitute in V squared, okay, the formula for it. Okay, and that's going to equal big G times the mass of the Earth times the mass of the satellite over R squared. No, I wrote S, R squared. Okay, so if we want to solve for the orbital period, we're going to multiply both sides by T squared. Okay, we're going to multiply both sides by R squared. So we'll have R cubed over here. Okay, T squared will be gone. And then we want to divide this stuff back over. So G times the mass of the Earth times the mass of the satellite. Okay, takes care of those things. And then we have to square root. Okay, so we're going to end up with the square root of 4 pi squared times 114,593 plus the radius of the Earth, because this is still an altitude and not an orbital radius. Okay, so we're going to have all right, so we're going to take that and we're going to cube it. Okay, and then we're going to divide that by what's on the bottom. Okay, and then we got to square root that. All right, so the orbital period of that X-ray satellite is 5.20 times, actually we have a lot of significant figures here, don't we? No, still only 3 because we use the mass of the Earth. No, we use the mass of the Earth, which only has 3. 5.98 times 10 to the 24, right? Only has 3. Oh, you know what? I got their 4.19. Did I punch something in wrong? I didn't. That's what it was. Yep, that's why I'm short. That is exactly what I did. I put 114,593 and I left it instead of putting 3 more zeros behind it. Yep, exactly what I did. Okay, you guys get the idea on the manipulation there rather than going all through it again? Okay, so how are we feeling about the satellite motion stuff? Are we feeling okay about it? Okay, it's starting to make some sense. I mean, really, they're all going to start out with FC equals FG, right? That's the only way to do it. Well, I mean, you could use Kepler if you're given the right information, but this always works, okay? So it's just a matter of, can I manipulate the formula? Can I get things moving around to the places they need to be? All right. All right, so what I want you to do is work on some of the satellite motion questions from the digital workbook. So I'll put them up here, okay? And then we'll go through any that give you trouble. And then tomorrow, okay, tomorrow you'll have a sub, okay, and they'll be doing playing the podcast and me going over gravitational fields. Okay, so I'll be explaining something else, and then you'll have some time to work on gravitational field strength and finish up the satellite stuff. And then Wednesday we'll do the we'll finish up gravitation, and then we'll review for our unit exam on Thursday because we'll be essentially done. Okay, it goes pretty quick. Okay, so the thing we need to know about gravity is that it is a field force. Okay, field forces are forces that can exert their influence without being in physical contact with the object that they are interacting with. Right? Other field forces would be electricity and magnetism. Right? A piece of metal does not need to be touching a magnet in order to be attracted to it. Right? An electron doesn't need to be physically connected to something positive like a proton in order to be attracted to it. They are field forces. They can exert their influence over an area or volume, okay, that they have influence in. No, gravity is the same, right? I don't have to be in contact with the Earth to be attracted to it, right? And same with the planets around the sun. If that wasn't the case, if gravity wasn't a field force, then nothing would orbit anything else. They would all have to be physically attached somehow. Okay, so gravity is a field because it can exert a force without being in physical contact with another object. Okay, and we measure gravitational field strength as acceleration due to gravity. Okay, so it's an acceleration. It's a rate of acceleration, right? It's not the force, okay? The force of gravity is different, okay? The force of gravity and gravitational field strength are not the same thing, okay? So Fg is not equal to gravitational field strength. And that is key because I often see people solve gravitational field strength problems by solving for the force of gravity, and they are not the same thing. I mean, certainly they're very closely related, but they are not the same thing. The force of gravity is how hard are two things being pulled towards one another. The gravitational field strength is at what rate are they accelerating towards one another. Okay, everybody follow me there. Okay, so one is a force and the other is a rate of acceleration towards one another. Okay, so for gravitational field strength, essentially what we're saying is that force of gravity equals force of gravity. Well, duh, of course it is. 1 equals 1. Okay, force of gravity equals force of gravity. But what we're saying really is this. Big G times M1 times M2 over r squared is equal to m2 times g, the smaller mass. Okay, the smaller mass times little g. This is how we can use Newton's universal law of gravitation to figure out what the gravitational field strength should be. All right, everybody all right with that idea? Okay, so if I manipulate this for g, for little g, all right, I'm going to divide both sides by m2, and m2 is just going to cancel. And that's what we're left with. We can calculate gravitational field strength by ignoring the second body because all things in the field at that distance would accelerate at the same rate, just like all things on Earth accelerate at 9.81 meters per second squared towards the center of the Earth. Everybody follow? Okay, so if we were to do this with Earth's numbers, what should we get, or should we get close to? We should get close to 9.81. So let's check and make sure that that's what actually happens here. All right, so we got 6.67 times 10 to the minus 11 times the mass of the Earth, 5.98 times 10 to the 22. And then we're dividing by the average radius of the Earth, 6.37 times 10 to the 6 squared. Well, I got -1. Well, okay, I get close, right? 9.81 is the average, okay, gravitational acceleration at all points on Earth. So, okay, this is going to be a little bit different. Okay, everybody all right with that? All right, so what we calculate when we calculate gravitational field strength, like we said before, is the rate at which the two bodies are attracted to one another. Okay, not the force that is attracting them, the rate at which they are attracted to each other. Okay, so we have Earth and the Moon. Do their gravitational fields overlap? They absolutely do. Okay, I mean, Earth's gravitational field is larger and stronger than the Moon's, but they still overlap. Okay, the evidence that we have of that overlap is that first off, the Moon orbits the Earth. Okay, but secondly, that on Earth we have tides. Okay, that shows that we're also caught in the Moon's gravitational field and that it can pull on the Earth as well. Okay, and there's a lot of kind of science and calculations that say that without the Moon, okay, the Earth would actually like speed up, and its orbit would radically change and things like that without the stabilizing influence of the moon's gravitational field on the Earth. So we're pretty dependent on the fact that it's here. Okay. All right. What happens if something gets caught or interacts with Earth's gravitational field? Let's say there's a meteor that's coming close to the Earth. It's not going to hit it, okay, but it's coming close. What would happen? Will its path change? Yeah, definitely. Okay, and that's what we see. I don't know if you guys have, like, sometimes someone will come up on Facebook or whatever, and they'll say, oh well, there's this asteroid and it's going to come really good. And there's all those like fear mongers out there who want you to think, the next asteroid that comes close to Earth is going to hit it, so you should like prep. And then they're usually the preppers, right? But in any case, anything that does come near the Earth is going to have its trajectory altered by the Earth's gravity. Okay? And so it actually gets, it's difficult to predict what something is going to do until it's closer and closer and closer. Their models become more and more accurate, okay, as the object becomes closer and closer. So, some guy who's got a telescope in his backyard and sees an asteroid coming towards the Earth, okay, he goes out and tells everyone the world is going to end, and then NASA comes up and does their calculations and their magic and whatever, and they're like, yeah, it's going to miss Earth by, like, it's going to be further away than the moon. Okay, but still, that's actually fairly close from an astronomical perspective. If an asteroid passes within the moon's orbit, it is well inside of the Earth's gravitational field, and its path is going to be significantly altered because of that. Okay, so as that starts to happen, okay, something that was moving in a straight line, okay, and wasn't going to be anywhere near the Earth starts to do this. Okay, well, it might get fairly close before it shoots off in another direction. Right? The big worry then is, what about the next time? Okay, we've altered this thing's orbital path. Where is it going to go now? Okay, is the next time it comes through on its way towards the sun, is it going to be closer? Okay, and so things like that have to be watched for, which is why NASA has an entire division called NEO, Near Earth Objects. Okay, they have a whole division of NASA that is responsible for tracking any and all objects from outer space that may come near the Earth. Okay, they are all labeled and they are all tracked by computer, okay, to make sure that none of them are going to get too close. Okay, sometimes they do, right? Anybody ever seen like meteors when they encounter the Earth? Right? Some of them, it's just a little shooting star, it's nothing. Okay, and sometimes they're big. Okay, anybody ever seen a big one? Yeah, okay. I've seen a big one. I was driving home from Cold Lake one night when I lived in Lloydminster, and all of a sudden off to the side, there's this bright, like flaming thing flying through the sky, and then it just disappeared. Okay, it was just a meteor that happened to be quite large, okay, that had probably just bounced off the Earth's atmosphere and went back out into space. Okay, and they do that occasionally. Right? And sometimes they get really close and we're not ready for them. Like the one that hit Russia there, was it 2 or 3 years ago now? Okay, a meteor came down and was close enough that when it actually exploded, it didn't impact, it exploded. It shattered windows and deafened a bunch of people and things like that. There may have also been a power outage, yeah, but I mean it was a pretty big disaster actually, because the meteor had gotten quite close for a meteor anyway. Okay. And then there's other evidence that we've seen that things like that have happened where for some reason a whole section of forest is all blown down in the same direction. Okay, there's lots of times evidence that there's been a shock wave from a meteor that got close to the Earth but didn't hit it, but exploded in the air and caused all the trees to blow down in the same direction. All right, so it is something that we have to watch for. Okay, the Earth's gravitational field can interact with other objects and obviously cause them to change path in possibly dangerous ways. Okay, we'll leave it at that for today. All right, so tomorrow you're going to go over this in detail, work on some gravitational field strength stuff. All right, and then Wednesday we'll do the assignment on gravitation. Thursday we'll do our unit exam review. Friday a little activity. Then you got your long weekend, and then on Tuesday probably start the next unit. Wednesday is your unit exam. All right.